I will talk about this R package called dynamite, which can be used for causal inference for panel data. I should sprinkle some Stan Bayesian things on the title. This is related to the conference. Yeah, so what is panel data? Well, basically we have data from n individuals. They could be persons or countries or firms or whatever, and we have multiple measurements over time for these persons. And here time can be thought as a calendar time, like month or year, or it could be the age of the person, or basically any other variable which somehow defines the ordering of these observations for each individual. And our interest is mostly in cases with relatively large number of time points, like 100, which is not much if you are working with some time series data, but we are mostly working on social science data where time scale is something like months, so 100 months is already quite a lot. And this is in difference to some other panel data models where you have something like T is 4 or something like that. And then typically we have multiple measurements per individual. We could have measured them or recorded their person's income or their health status and partnership status, where do they live and when have they born and so on. So often you get this kind of data from some registers and things like that. And what you would like to do with such data, well, of course it would be nice if we could do some causal claims, and that's what we are after. So given the sort of broad definition of panel data, you can of course think lots of different methods statistical methods you could use to analyze such data, and different fields have different conventions, what kind of models they tend to use. And there's no one correct way of doing it. It should of course depend on your data, both the observed characteristics of your data and the assumed causal graph or the data generating process, and what's your research question. And in many cases these kind of panel data models are estimated using some variant of maximum likelihood, like restricted maximum likelihood or something like that, but of course here we all want to do Bayesian stuff. Just a small note that some of these models, like obviously hidden Markov models, for example, are often formulated in a latent level. So we assume that all the cross dependencies between our observed variables are actually defined on the latent level, and then given the latent processes, we just observe something conditionally independent. This is computationally often nice, for example, in point of missing data and things like that. But from a causal perspective, it can be quite annoying. How do you then make the causal interpretations? But I'm not going to talk about that now. So here's one kind of a directed acyclic graph of this kind of panel data with three different variables. What is it? Z, Y, and X, and at time t, all of these X affects all of these different variables at next time point, and similarly for Y and Z. And of course there could be a longer time dependencies as well, or some of these arrows could not be there. And our interest is in something like, what if we do some kind of intervention here? What happens, for example, Y at time t+2? So in this R package dynamite, we implement something called dynamic multivariate panel model, which is at least somewhat flexible approach for this kind of data analysis. So some of the features of this package or these models is that we can model multiple response variables with different distributions. So we could have, for example, Gaussian observations and also some categorical observations from the same person, and how these are then linked together. Then we can, of course, have time invariant effects, so basic regression effects, and also time varying effects, where we assume that the effect of some covariate or some response to some other response varies over time based on a Bayesian p-spline. And then, as in multi-level models, we can have individual level effects and also something called common latent factors. And everything is done in a fully Bayesian fashion using Stan on the back end. So then instead of just point estimates, we get the full posterior distribution of the causal effect or this intervention distribution. The package supports both R-Stan and common Stan R. Of course, we would like to use just common Stan R, as that's in many ways much nicer, but unfortunately that's not an option in many cases when we are dealing with these private register data servers where you can't install anything outside of CRAN. Yeah, and we do support both within chain and of course between chain parallelization, and there's automated functions for both leave one out cross validation and leave future out cross validation. So now we get into the causal things. What's causal about this? Well, our approach is based on something called structural causal models, so Pearl's DAG-based causal framework where the causal effect is defined as an intervention. So we make some kind of external change to the data generating process and then see what happens because of that. And the first step is, of course, to come up with the correct causal graph, and that's maybe the most difficult thing to do, where you need some domain knowledge and prior knowledge and things like that, and then everything conditioned. If we sort of trust that graph, then given some additional steps, we can claim that our results can be interpreted as causal. So basically, when you do the graph, then you can use these graph theoretical methods to find out whether your causal effect is so-called identifiable, and if it is, then you can think that, okay, what's the good parametric or non-parametric statistical model for that, and then you can, for example, use the dynamic multivariate panel models. And then the final causal effect estimate is a function of the model parameters, but the model parameters themselves doesn't necessarily have a causal interpretation, and at least an easy one. So we use those models then to simulate the posterior distribution of this interventional distribution, this P, Y given do X. And something which we are especially interested in is something called long-term causal effects. So let's say we do some kind of a policy reform or some kind of intervention at this year. Of course, it's interesting to know what happens immediately or next year, but often the interest is also in what happens in year 2, year 3, year so on, like the long-term effects of some let's say some tax code changes or something. And in order to estimate this kind of effects, you basically have to model all the endogenous variables in your graph, because they are like the intervention to the affects the next response variable, and maybe the response variable affects the next something else, and so forth, as I showed the DAG earlier. And in order to do this kind of modeling or estimate these kind of causal effects, you basically have to simulate forward over time in a these kind of counterfactual predictions. Yeah. And there, of course, Bayesian stuff is nice, as we have these posterior samples. Here's a very simple example, chosen mainly because the data is freely available in this RPackage March. So we have data from almost 900 individuals, and every 2 years they were asked what was their work status, whether they were working full time during that 2-year period or not. So it's just a binary variable, and then we can think that, of course, your work status probably depends on whether you were working on the previous time point, and also the whole work history might affect your probability of getting employed. So whether you have ever been full-time employee or not. And then there's only one time invariant covariate called gender, and this is our causal graph. Basically, there's only 3 variables: the gender G, and then there's the Y, which is the full-time employment, which depends on the previous status, and then the work history, which is basically a deterministic variable. If we know the previous value of this work history and the current work status, we know exactly what's the work history at that time. And the causal, because I don't really believe in this graph, and neither should you, because of course the actual phenomena is much more complex. You should have education and all kinds of things here. And how you would model such data or graph in this dynamite package. It's quite small, but anyway, it's the normal, relatively normal R formula syntax. So we have these ops functions, which defines these stochastic normal response variables. Here, the full-time employment, and then we have the aux, which defines these auxiliary responses, these deterministic response variables. And why do we do it like this instead of just pre-computing the work history and putting it as a covariate? It's because in order to make these dynamic predictions, this way we automatically update this variable during the predictions. And then there's the varying component, which defines which of the variables might have a time varying effect, and then there's some other additional things we need to do. Yeah. And then you just call the dynamite function with some arguments to stan and get the model fit. And this is ugly, and I have too little time. But anyway, we can use so-called backdoor formula or adjustment, where we have part from our model fit and part from our data, and then we just call or make 2 kind of a counterfactual data sets, where at age 30 we put the person as a oh yeah, I forgot to say that we are, oh no, it's going the wrong direction. So we are sort of pretending that we are interested in making this kind of a intervention at age 30, that let's put everyone hypothetically out of work or to work, and see how the future shapes. So we make these two data sets where we put everything missing after the age 30, and this is just dplyr code. We call the predict function twice, and this is the result. So the effect of being full-time employee at age 30, it still has an effect on the future employment probabilities at age 44, although it decreases over time. Yeah, but you shouldn't trust this too much, because the graph was way too simple and the data was too simple. Anyway, yeah. Yeah, thanks. Then I have some additional stuff, but I think I'm running out of time. Yeah, thanks.